Alright guys, my name is Juan Ortiz and today I will be talking to you about our code for this project 2 that we had. So for the first problem, we had to, well first of all let me explain a little bit about the background. So as you know, MATLAB isn't just used in the engineering field, it's also used in applied mathematics. At one point you will use MATLAB in your career, and it will likely be in finite element analysis, so that's going to be a future class that we're going to be taking as engineers and me as a mechanical engineer. So this is important for things like differential equations, numerical analysis, linear algebra, computing, even bioimaging. So those are some of the things that we will approach today, mostly just the linear numerical analysis section. So for the first problem, we had to have, okay, so as the problem statement says here, the linear systems of equations are things that are used in these engineering fields. They're sophomore level classes. So as you know, we're going to have two different functions. The first is going to be a matrix function that'll convert a function that'll convert the matrix to the upper level triangular form, which is this up tree here. And this function is the one that's going to create the matrix. And then we're also going to have one to take the output of the first and solve the equation, which is going to be our back sub. This is the function that's going to work to have the solution towards the end that we want to have. And this is to solve the linear systems, the first problem in our group project. So here we defined our variables. T is the matrix, U and X are going to be our functions, and this is the solution that the MATLAB code, MATLAB was provided. So as you can see here, we'll run the test. First we'll start with the while loop, and we'll have it check that it's a n by n plus 1 matrix. That's the only way this can work. Then we'll have the size. If the matrix isn't n by n plus 1, then we'll have it say that it's not by putting an fprintf statement. And if it is, then we'll end the loop. And we'll display the matrix T. After that, we will have the uptree function and the back sub function to solve our matrix. And then towards the end, we'll have also the MATLAB command. So in the end, if you want the program to restart, 1 means yes, 0 means no, and I'll show you right now. So if we run this code, so it asks us to enter an n by n plus 1 matrix. So let's say we do 1, 4, and let's say we end it there. So again, here we're going to have uptree is 1, 4, so that's our matrix. Our back sub is going to be, hold on, my bad. Our back sub is 4, of course. The solution is going to be 4, and if we want to restart it, 1 means yes, 0 means no, so if I put 0 here, okay, my bad, that one's a mistake, let me run it again. Okay, so let's say we have 1, 4. Okay, so then I enter here 0, that means no, it'll end the code. Now if I want to run it again, I put 1, 5, let's say. So let's say I want to put another one, I just enter 1, and it asks me again. And here, let's check if it'll accept something bigger than n plus 1, so there. And of course no, because this is not correct. The size of the matrix is 1 by 3. Please try again. So again, let's try 1, 6, 7. It won't accept it. Okay, what about 1? It won't accept it, even accept sees that it's 1 by 1. So that's for the first one. You can try negative values, -5, -7. And here's the solution. So we have back sub is 1.4, and if you want to restart it again, 0, no, okay. So this one works with any n by n plus 1. We could try a bigger matrix. Let me run it again. Run section. I should just press 1. Okay, so enter an n by n plus 1, so let's say 2 and 3, and then 5 and 6, and then 7 and 8. Okay, it's not correct, so then 2 by 3, let's see. 5, 6, 7, 9. And so here you see the solution is negative 1 and 2, and if you want to restart it again, I'll just put 0, and there it should go. And then for the second, let's see. For the second problem, we had another numerical analysis problem. And this one, we were supposed to develop a bisect root, which is a function that's going to take the input vector and for each form of a vector that we have as input. And it's going to get each constant that corresponds to a, the coefficient of that order. So if it's, let's say if it's the first one, a is going to be to the highest power leading to the last one being to the lowest power. And even if there's a skip in that one or something at 0, then we're still going to continue that order, that coefficient. And it's going to take the maximum acceptable error in the solution, so that's the one that you input, and the starting two bounds. So that's going to be a lower bound and an upper bound. And it's going to show what we want to output is the approximation of the root, the maximum error of your solution may have. And so let's start by defining our input variables. So the first one we have is a, which is our vector. T is going to be the tolerance that we put in. LB is going to be the lower bound, and UP is going to be the upper bound. So our first task here is to define our output variables. So we start with housekeeping commands, of course, and again we start with this while loop in which we're going to input a 1 by 1 vector. So here, if we don't have this, this size here is going to say that the row needs to be a row vector, so we're going to try again. And if we have a size that's too large, the size vector should be greater than 1 in this case. So, and then in the end, if we have it correct, we end the loop. We're also going to check that we're going to input the tolerance, and if they enter a tolerance that's a vector or a matrix, we're going to state that we need a scalar value, so we want the size to be 1, 1. And we end it there. Again, we're also going to have to input lower bounds and upper bounds, and here we also put that we need scalar values, not vectors or matrices. And then we're going to have our function, which is bisect root, which is this one right here. So this one's going to have the initial variables, the approximate root, the maximum error, and the number of iterations. And we start with the 0. And then we start a statement with lower bounds and upper bounds. So if the lower bound is greater, then we're going to state that the lower bound has to be smaller than that upper boundary. So we have to have one that's a lower bound has to be smaller than the upper bound. And so we have our function here with the lower bound and the upper bound. We also have to make sure that if the lower bound is positive, that the upper bound is negative, and we can't have them if they equal 0 in this case, then we have our approximation root equal that, and our maximum error also equal that. So here we have the tolerance, and this is going to help us find the number of iterations and the maximum error. So let me go back to our code. And then we're going to run both the bisect root, and then once we run it, we're going to have the solution, the number of iterations, and the maximum error displayed. And we're also going to have a question if we want to rerun this application, yes or no. And let's just try it out. So I'm going to put run section. So, okay, wrong one. Section. Okay, so enter n by n plus 1, so we have 3, 4. Okay, so now it's going to say, since, sorry, it was all in one code, so now let's say enter a 1 by n vector, so this is going to be a straight vector. Let's try putting first 2, 4, 5. Let's see if this will run. No, so we need a row vector, of course, for this one, so we try again. And put -7, -8, and 0, 9, so make sure we're not hard coding anything. Again, it'll ask to enter a row vector, so we go ahead and we enter 3. Okay, I close that. So now I'm going to enter the tolerance. Let's say 0.01 is going to be our tolerance. Our lower bound, our first lower bound should be, let's say 0. Our next lower bound is going to be 5. So here it'll display again the value for that function at both boundaries is positive, and it will ask us if we want to restart again. So let me put 1 for yes. And again, it asks for entering an n by 1 vector. A equals, let's say, 5, 6, 7, 8, 9, 10. All right. So again, this is going to correspond to the highest power being 5, 6, all the way down to 10. So this is going to be 10, 9x, 8x squared, 7x cubed, 6x to the 4th, and 5x to the 5th. Okay, so our last ones are constant. This one's going to be to the 5th power, because this length is what's determining how our function is going to be. So let's enter tolerance. Let's say now I want to put 0.1. Okay, lower bound, let me put a negative here, -3, and then a positive 7. So here, it'll give us okay, so this one worked. It's going to give us a solution, a -1.2031. That's the solution for our equation. The number of iterations it had to do was 7, as you can see here. Then the number of zeros corresponded to the lower bound being -3 and 7, and here you can see how it goes through each iteration, showing you the x values, the function, and the maximum error that each one has, up until the last one, which is the one we're looking for, right? And so if I want to restart, I put 0, and then it'll just give me again, enter, I think I might have entered 1. So enter 1 by 1 vector, 2, 3, 5, 7, -9, 0. Okay, so this one means that the 0 is a constant, so a tolerance of 0.2, let's say. So -8, and the lower bound 9. And here again, here it displays, okay, awesome. We got the figure to display. It's going to display our maximum error versus the number of iterations. That's our figure that we want to see. And here you can see that the maximum error is this curve here, and the one we calculated up to the second iteration started following that maximum error curve. Okay, so now we can close it, 0. Awesome. So now you can see here, this is our part of our second project, the numerical analysis. I hope that you found this kind of like, I guess, a good explanation for this code. I hope that you like our video, and I hope that you get to understand our code a lot better once my explanation went through and with our individual projects. I thank you for your time, and yeah, have a good day, a good night.